Welcome. In this video we're going to be going over the background behind a CB or Citizens Band radio. So starting with the general process of it, as if you were going to transmit, you talk into a microphone. So a microphone is a transducer. What this means is that it converts one form of energy into another. So in this case we have a diaphragm, a piezoelectric diaphragm that's converting the sound waves from your voice into an electrical pulse. So piezoelectric, Greek word piezo means pressing, so it turns a mechanical force into an electrical pulse current. So what it does is you talk and your voice, the sound waves, vibrate a diaphragm, which is a piezoelectric material that generates a current, which then goes to the ferrite duplexer. So you can think of this sort of as a switch, obviously made of iron, ferrite. So what it does is it can extremely quickly switch between taking in input from your antenna and sending output to the antenna. So this will basically know when to allow output towards the antenna when it comes from the microphone, so that way you're not always getting like feedback, not trying to push like signals two ways. So then from there we go to our radio wave generation. So this is either transistorized in modern things, or it could be done by a magnetron back in the day, or like in microwave ovens. Could do a whole separate video on how these work, but anyway. And then eventually the electromagnetic wave gets radiated outward from your antenna. So moving on, so a CB radio has a bandwidth of 40 channels. Well, sorry, the bandwidth is 26.965 to 27.405 megahertz, and there are 40 channels within that range. So going into the equation, velocity equals frequency times wavelength. So this velocity is the speed of light in feet per second, so that's 9.83 times 10 to the 8th. Should be equal to this frequency I just chose in the middle of this range, so just say about what would be channel 20 maybe. So 27.195 megahertz times wavelength, we get a wavelength of 36.17 feet. So this is going to come up later, this is going to be important. But anyway, so antennas are always built to be fractions of that wavelength. So example, you'll find 5/8 of the wavelength, 1/2, 1/4, 1/8, and you'll see when you buy your antenna, it'll say like 5/8 antenna, 1/2 antenna, etc. So just for example, so a half antenna needs to be about 18.09 feet, and an eighth antenna needs to be about 4.52. And so you might be thinking, oh, well, I'm buying an antenna, it says it's, say, somewhere in 2 to 4 feet. But what that really means is, so if you bought a 2-foot antenna that was rated at a half a wavelength, it means it would have that 18.09 feet of wire coiled around inside it. And when you're tuning your antenna, what you're really doing is changing the length and the resistance, which is important for the standing wave ratio, which we're going to get into right here. So a standing wave ratio, or standing wave, stationary wave. So what causes this is basically impedance mismatch is the basic thing. So all of your equipment is designed to operate at 50 ohms, so resistance of 50 ohms, resistance, impedance, same thing. And so say in reality, eventually your equipment hits another wire that has a resistance of 100 ohms. So what's going to happen is this change in resistance, this impedance mismatch, is going to create a reflection of that signal, right? So this is the standing wave pattern, right? So we have the wave traveling and then it reflects, and this creates destructive interference. So you don't want that. So in this case, with 50 ohms and 100 ohms, our SWR, our standing wave ratio, will be 2 to 1, and so that's possibly acceptable. 1 to 1 is obviously perfect, and when you get above 3 to 1, usually your radio is just not going to work anymore. You're not going to transmit or receive because too much of that energy is going to be lost with that destructive interference. If this were, say, 150 ohms, too much of that energy would be reflected back and you wouldn't get anywhere. So again, tuning your antenna alters the length and resistance. That way you can change your SWR. SWR is a very important thing. When you're setting up a CB radio, you need an SWR meter to help you tune it appropriately. So again, more resistance will mean less power. So your CB radio is already limited by the FCC to 4 watts, and by design it's capped by, you can't go less than 50 ohms because all of your equipment will be built to that spec, right? So if we look at power equals voltage squared divided by resistance, so we're already limited here with 4 watts and 50 ohms. So again, basically, if resistance goes up, power goes down. So you want to make sure that when you're buying your coax cable, you get a coax that's rated at 50 ohms. So the RG58 is the most common one, and that's pretty much what you want. Again, you don't want a coax with a different resistance. So moving on to noise and squelch. So when you think about it, there are electromagnetic waves everywhere, all the time, and you don't want your antenna always picking those up. You'd get too many things. It wouldn't be anything useful to you. You just get all kinds of noise, all kinds of static coming through your radio. So that's where the ferrite duplexer can kind of help by not always taking in noise, but also squelch is a term. So usually on your radio you'll have a little knob that will help you adjust the squelch. So the squelch is basically a noise limiter. So if we look at this little graph I made here with signal strength and voltage to time, so this would be like your antenna's always going to be picking up a little bit of signal, but that's just noise. You don't care about that. So the squelch preset will only output a signal to your speaker, so you'll only hear something if it's above a certain level, and that's what you want. So right here, this would be the actual signal that you'd want to hear, and that would help with that. So moving on, gain is another term. So this is the directionality of your antenna. So a quick picture to help you kind of understand that. So a high gain antenna, so if this little thing right here is the antenna, it's kind of very focused in where it's emitting its radiation. And a low directional antenna will just emit it equally in all directions. So you can calculate that with your maximum radiation intensity over your average radiation intensity. One more term you might want to know is your ground plane. So if you're installing your CBE in a car, which you probably are, the ground plane basically is your car. So it's basically a reflective metal surface that will really help your antenna pick up signals. So if you had signals coming in, this being the metal ground plane, it'll help reflect those waves into your antenna, or if your antenna is transmitting, it'll help reflect them up away. So you want your antenna a bit above the ground plane. So that's just another important term. So one last thing, so we're going over here, so we look at some common codes. I'm not going to read these to you, but these are common things you might hear people say over the radio. Some common channels, so 4 is often used for 4x4 vehicles, 9 is for emergencies only, and 19 is common for truckers and traffic talk. And lastly, so we'll do a little electromagnetic spectrum comparison just for fun. So an AM radio operates between 540 and 1600 kilohertz, CB 26.965 to 27.405 megahertz, FM 88.1 to 108.1 megahertz. Your internet router is 2.4 gigahertz. A lot of them also have an option for 5 gigahertz, but usually in modern routers you have both. And your microwave oven, very similar, 2.45 gigahertz. So the lower the frequency, the longer the wavelength, and the farther the wave can travel. So that's why, like on your internet router, the 2.4 gigahertz will actually travel farther around the house than the 5 gigahertz one will. But the 5 gigahertz one carries more energy and is faster. And that's about it. Let me know if you have any questions. That kind of sums up the Citizens Band Radio. If you feel like anything needs more explanation, let me know. Thanks.